Okay. So I think most of you have got the response like this 0.0405, right? Based on the last class idea for base conversion in per unit domain. Now we want to see the scenario for diagram concept. Diagram concept like single line diagram or one line diagram addressing issue. Regarding the diagram aspect, from single line to actually yes, yes. Anyone? Any question?
Sir, sir, একটু slightly একটু zoom out করে 1 থেকে 2%. হ্যাঁ।
বুঝতে সমস্যা হচ্ছে? Zoom out। তো 120% আছে। 120% zoom out করলে তো আবার কন্টেন্ট দেখতে পাবে না। Is it visible or problem?
না স্যার ঠিক আছে।
Okay, fine.
Yes, sir. Is it visible?
Regarding the per unit notation, as already mentioned, when you have some generator or motor like rotating device, you have to use the circular notation inside that. If it is generator G and M or motor scenario, two winding power transformer, it is actually already you have the idea of that symbol in last semester also for the transformer case. You may have sometimes these types of three core transformer also. Actually, three winding transformer is not the idea for this class. Fuse may be there based on the protection purpose, current transformer. These are the different symbolic representation for single line diagram. Power circuit breaker, air circuit breaker. There you have some circuit breaker which has the extinction medium is air, free air. Three-phase, three-wire delta connection, Y connection, this is already known to you, Y delta configuration for the circuit. Regarding the Y configuration, you may have Y without the neutral wire. You may have sometimes Y considering neutral grounded. Neutral unground situation may have also neutral grounded situation in the neutral ground. You have sometimes solid ground. In some case you may have reactance ground. That means in the neutral path, to limit the short circuit current or the unbalanced or fault current, you may have sometimes reactance in the neutral ground path. Okay. So regarding Y configuration, you have three different options. Potential transformer, okay, fine. Ammeter, voltmeter, these are the meter part. So if we have some diagram, something like this, can you configure that diagram to its equivalent? This is actually the single line diagram, okay? Single line diagram or per unit or it is the one line diagram. So what are the components attached to that diagram? We have in the left side, we have two generator, right? Two generator, one load attached to this bus, left side bus. Then you have, these are the isolator or the protection block. Isolator there. There you have the transformer which has YY configuration of transformer, and the generator you can see in generator it is actually you have some reactance in the ground path. as well as some resistance ground. But for transformer, you have solidly grounded in the Y configuration. So these are different option you may have sometimes. And in the right side, you have another transformer where you have Y delta configuration. Actually in the transformer, as you have the idea, there might have YY configuration like T1. You might have Y delta configuration like T2. And the phase group or vector group, it was discussed in last semester, and phasor analysis like YD1, YD11, DY1, DY11, or YY6, YY, DY, DD6, like that. So based on that phase option or the configuration between Y and delta, you have different phasor angle or vector group. In the This is the protection for isolating, and this is the other generator in the right bus as well as load that right bus. So these are the power single line diagram, right? This is the single line diagram. This single line diagram, you have to switch to its equivalent, actually impedance diagram, without the value or without the information. Can you shift that information of single line diagram to impedance diagram based on actually the configuration of generator, load, as well as transformer? What you have to do, in the left side you have generator, and this generator internal configuration or generator has connection to the ground. So it is actually, if we just want to draw the equivalent circuit of the generator, what we have to do, we have to include one reactance or impedance attached to the generator in series, right? So two generator will have the configuration of series impedance or series reactance. Load, if we just consider load as RL or RLC, based on the factor of whether it is lagging, leading, or sometimes in the combination of RLC, you can use the load. As well as transformer. For transformer, actually, you know the equivalent diagram of the transformer by this time, I think. Equivalent diagram. So we can see the picture in terms of, this is the per phase impedance diagram without having the information. Actually, just now what we have mentioned, here you can see E1. This is the first generator, right? If we just split the diagram, this part, that means up to this point, what is there? We have two generator, right? That generator has neutral path, grounded, and in the generator you have the internal resistance and impedance, that means the reactance, as well as for load, the resistance inductive load. And for this is the transformer T1 part, where you have the equivalent circuit, something like this. That means you have the core loss path, copper loss path. These are the path, the shunt path, and you have some resistance and inductive configuration. That is the impedance for what we can say, the input impedance or the primary impedance for the system. And this part you can consider as secondary impedance, which is converted to primary side. Okay. So this is the transmission line, and regarding the transmission line, the resistance and impedance, the inductances are in series and capacitance are in shunt branch. And in the right side we have the transformer again, like T1, here it is T2, and this has the load side, which is B, load side RL, and generator, which has also the generator configuration, like the left side, two generator for left side, one generator for right side. So this is actually which diagram, this one, this is the impedance diagram, right? All the resistance, and you have the capacitance as well as inductance, which is in series. So all the informations are there. This is the total picture. Okay, but for simplified response, we can consider the diagram in reactance information, something like this. This is the simplified reactance diagram, per phase reactance diagram. Okay, here we don't have the resistance, only the reactance components are there, attached to the generator, and we don't have considered the load. For transformer, only the uh, inductance, line inductance, uh, as well as this is the right side transformer reactance, okay, X, and this is the generator of right side. So this is the simplified reactance diagram for the system. Okay, so by this time I think you have got the idea clear, right? What do we understand by different diagram in terms of simple or the general information from per unit impedance or reactance diagram, or single line diagram to per unit different arrangement like impedance or reactance diagram. Okay, now we want to observe the case for, is there any confusion regarding that single line and the impedance and reactance diagram? Which part? For single line diagram or impedance or reactance diagram? Do you have any question for this part? Because when you solve the calculation, that means after per unit information, you have to draw the diagram correctly. Okay. That's the
So reactance diagram.
regarding reactance diagram. Okay, fine. This is the reactance diagram, right? What's your question? Yes. What's your question? Or
মানে স্যার সবগুলোকে ইগনোর কেন করলাম? মানে স্যার
yeah,
লোড, রেজিস্ট্যান্স, শান্ট এগুলোকে কেন স্যার ইগনোর করলাম স্যার? মানে রিমুভ কেন করলাম স্যার?
regarding that reactance information, actually that reactance diagram sometimes we can consider as positive sequence network, which has only the generator information. Okay, only generator information, excluding all the other information. Generator, how many generators are there, and here is actually this is actually transformer and line. Okay, excluding the uh, receiving end or load side, only the generating information you have to consider for reactance information for reactance diagram. Loads, resistance, as it is reactance diagram, you can simply omit the resistance part and the shunt branches for the uh, Actually, this is the simplified version of the impedance diagram. So only this consideration you have to think for reactance diagram. Yeah.
স্যার ইম্পিড ডায়াগ্রামে কি বলতে গেলে যে আমরা যে ইম্পিডেন্সের রেজিস্টিভ পার্টটা ওটা বাদ দিয়ে ডায়াগ্রামটা আঁকতেছি এটাই তো?
No, no, no. Only the resistance part না, এখানে তোমার shunt admittance টাকেও ignore করা হচ্ছে. We have ignored the shunt admittance also, okay? As well as load. This is the resistance. This you have to exclude as well as shunt admittance and load. These three things you have to remove from the circuit to draw the reactance diagram. Okay.
স্যার
Yes.
স্যার
Yes.
স্যার উপরে যে তিনটা কয়েল আর কি ও দুইটা তো ট্রান্সফর্মার রিপ্রেজেন্ট করতে স্যার আরেকটা কয়েল কি রিপ্রেজেন্ট করছে?
আরেকটা line reactance. This one is the line reactance. Okay. Line there
Yes,
is
sir.
also resistance and shunt admittance. This part you have excluded, only the reactance part of the line we have considered. Okay. T1, T2, and this one is
Yes,
the
sir.
line reactance. Okay. Is there any other question from your side? Okay, fine. If you don't have, in that case, we may proceed for other topics. Another important aspect for the system. Now we want to observe the scenario for nodal equation application for the network. Like this is the topics. If this is the circuit, okay, this is a circuit. The circuit which you have already the idea, the simplified circuit solution or the nodal equation. We want to recall the nodal equation concept for circuit. Okay. If we think of that scenario, how many nodes are there in that diagram, given diagram?
4.
4 node, right? 1, 2, 3, 4. As actually 5, 1 considering reference, right? When we apply the nodal equation or nodal solution for the circuit, we have to consider one reference node. Okay. The ground or the neutral path, the lowermost node we have considered as 0 or reference node. So based on that reference node, can we write nodal equation for node 1 considering
Yes, sir.
admittance expression? Try to write the nodal equation for node 1. Or can we write for node 3? How many branch are attached to node 3? 1, 2, 3, 4, right? 4 branch attached to
Four.
node 3. Yes. 4 node branch, 4 branch attached to node 3. Out of them, 1 is current source out of 4, and 3 are the admittance. Actually, when you draw or write the nodal equation for any circuit, those informations are given in impedance notation, right? But here you can see the informations are in admittance. So can you write the admittance nodal equation? This is the actually simplified version, or it is actually easier version of the nodal equation to write for node 3 or node 1. On node 3, try to write the nodal equation as well as, yes. Yes, who?
Sir, what figure is this?
স্যার কোন নোডের জন্য বের করব?
Node 3 as well as node 1. Actually, you have to write all the 4 node, okay? First node 3. Start from node 1 or 3.
ওকে স্যার।
Right
Sir,
nodal.
what figure is this?
Yes. This is circuit.
Sir, I assume,
Hello.
sir, is it related to that circuit that we have seen in the transmission system? I mean, the generator and the transformers?
No, no, no. It is the different. This is the other topic. We want to solve the nodal equation to
Okay,
form
sir.
the other aspect, not the earlier diagram. Okay, this is the different one. That the reactance impedance information diagram is already completed. Okay, this is the new one. If it is the circuit, can try to write nodal equation for node 1 and 3 as well as 2 and 4. Considering the lowermost node as 0 or reference node. For node 1,
Sir,
what will be? Yes, who is there?
what is the name of this figure? This circuit diagram,
Yes,
I mean, what is the name of the circuit, this circuit you draw?
it is the simple circuit, right? You don't need to think of this is the uh, admittance diagram you can consider. Admittance diagram. Okay. Or circuit, simple
Okay,
circuit
sir.
diagram. Admittance diagram or simple circuit diagram. Because all the informations are given in admittance domain. Okay, not in reactance or impedance. This thing you can consider as admittance diagram.
Okay, sir.
If you have been given some admittance diagram, can you write the nodal equation for different node using the KCL concept? Try to write the nodal equation for 1, 2, 3 as well as 4 node. Okay. For node 1, you have V1, V3. Okay, fine. YC. V1, V2, V1 minus V2, YD. V1 minus V4, YF. Minus. For node 3, V3, V3, YA. Okay, fine. V3 minus V2, YB. V3 minus V1, YC as well as minus I3.
স্যার নোড 1 আর নোড 3 বের করেছি নোড
Okay,
2
you
আর
have to
4 বের
complete
করব
also 2 and 4, right? 2 and 4. Try to find also 2 and 4. Regarding the nodal equation writing 203, try to write the voltage current in one side and current if there is any current source in other side of the equation. Okay. If the equation is correct, but
So
for
ultimately,
yes, the equation is okay, but the formation you have to write like that so that when we want to form the matrix, it will be better or easier. Only the current in other side. Okay. 229, I think it's okay. So when you have completed the equation, it is simple equation like this, right? V1 minus V3 YC, those who have already determined V1 minus V2 YD, V1 minus V4 YF for node 1, because they are attached to node 1, the 3 branch. So when you write all the 4 node equation, you have to isolate the voltage. That means you have to form, you have V1, V2, V3, V4 in all the equation. Okay. Try to regenerate the equation or rearrange the equation in terms of voltage. All the information after writing all the nodal equation for 4 different node, first of all write 4 different node equation. Node 2, okay, fine. So when you complete the nodal equation for all nodes, that means 1, 2, 3, 4, try to rearrange all the 4 equation in terms of V1, V2, V3, V4. Okay. This will be the next step. First step, write all the 4 node equation. Second step, rearrange all the node equation to V1, V2, V3, V4 orientation. And if there is any current source in other side of the equation, rearrange the 4 nodal equation for node 4 node in terms of V1, V2, V3, V4.
স্যার মানে কি ভোল্টেজ গুলো এক সাইডে রাখবো আর কারেন্ট গুলো অন্য সাইডে রাখবো?
Voltage you have to rearrange in terms of voltage. That means V1, what is the V1? V1 with attached to actually Y. That means if you have any equation, try to assimilate all the V1, okay, V1 into some Y, then V2 into Y, V3 into Y for all equation. The equation what you have derived or what you have generated, it is in terms of Y, right? You have to switch that in terms of V1, V2, V3. Rearrangement. Take common of V1. What is there in terms of V1? What is in terms of V2? Like these are the all equation, okay? And when you arrange that, all the V1 should be taken in terms of Y1 like this. That means you have those equation, rearrange those equation in terms of this one, right? You have V1 and then all the Y. Taking all the Y in terms of V1 for node 1. In node 1, you have 3 V1, right? Rearrange that equation like
Yes,
this.
sir.
Yes.
In terms of V1, V2, V3, V4 like this. That means you have already the equation in your hand, rearrange that in this way. So that some.
Sir, can you scroll down? I have a little confusion, sir.
Where? There?
Sir, the math equation.
Which one?
Sir, here it is y1, y12, something like this. But at node 1, we get that V1 has 3 y components, right?
Okay, don't need to think of this matrix right now. Just rearrange your equation. Then I will discuss that. Okay. The equation is
Okay, sir.
already in your hand. Rearrange that in this way. I will discuss that later. When you complete that job, this what does it mean by y11 or y12 or y13? That will be discussed in next phase. Okay. First, formulate that. The coefficient attached to V1 will be considered as y11. That means all the three equals y11. As well as the coefficient of V2 will be y12, considering negative as coefficient. So when you complete all the rearrangement for 4 equation, uh, that orientation of first equation, if we just consider of rearrangement of first equation, the y11 will be all the coefficient attached to V1. That means what you have got from equation 1, what are the coefficient attached to V1? 3 coefficient, right? Which is YC,
Yes, sir.
YD and YF. So that YC, YD, YF, the summation of all the three will be Y11. Okay. All the coefficient information. This is the uh, self admittance of the node 1, Y11 means. Okay. And this is the uh, actually you can correlate that idea that all the coefficient of Y11 is attached to what about y12? Y12 will be the coefficient of V2 in equation 1. Okay, that will be minus YD, right? Minus YD. Y12 will be minus YD. Only one component which is attached to V2 in equation 1. That will be the mutual admittance, self admittance and mutual admittance. So this is the summary. When you complete all the nodal equation, the equation will be something like that, right? This is the final version of all the y, and that is known as y bus matrix. That means the coefficient of all the admittance in matrix orientation. This thing you can consider, and from that chart I can say what is the coefficient of second equation or third equation or fourth equation. Like node 1 equation, V3 coefficient will be minus YC, right? If you have solved the equation correctly, it will be minus YC, which is attached to V3, and minus YF attached to V4 for node 1 equation. Okay. So this is the summary of the admittance information, which is in matrix orientation, and that is known as the Y bus of that circuit. Okay, from the admittance diagram of the circuit. The admittance information will generate the Y bus matrix based on KCL concept or the nodal equation concept for different node. Okay. Then for node for node 2, if you write the equation for node 2, the coefficient of V1 for node 2 equation will be minus YD. Is it correct?
Yes, sir. Minus YD.
Okay, right. If you solve properly, it will be minus YD. Regarding node 2, the V2 coefficient will be the summation of three component YB plus YD plus YE. This is the self admittance of the node 2, which is attached to V2 coefficient. Okay. So one interesting thing is the self admittance regarding the node which is Y11. Okay, that is addition of all the admittance attached to that, right? If you can check, it will be the addition of all that, and self admittance will be the positive. Whether the mutual admittance, which is actually, if you consider node 1, this is the coefficient of V2 is negative. Okay, so the diagonal matrix, here it is the diagonal matrix, it is for self admittance, information of the admittance diagram, and the other remainings are off diagonal matrices are mutual admittance. Okay, mutual admittance have the negative polarity. You can see the mutual admittance, all the mutual admittances are negative polarity. One interesting fact, what about node 3 equation and the coefficient of V4? Is there any V4 coefficient in node 3 equation?
No, sir.
No, that means you don't have any coefficient. That's why it is 0 there. Okay. 0 for node 3 equation and V4 coefficient. So this is Y34. Y34 will be 0. Okay, this is the Y34. That means this is for node 3 in terms of V4 coefficient. If you can just think of that interpretation of admittance, the first notice, the subscript first point is the node, and second point is the coefficient of the voltage. Okay. So if we can think of Y31, we can interpret that, right? Y31 means this is the node 3 equation. The first of subscript is the node 3. This is the node 3. And 1 means the coefficient of V1 in the third equation. This is the Y31, which is actually mutual admittance because it is Y3 and 1. If it is Y11, it is the self admittance. So this is the admittance matrix formation of the given admittance diagram, which is Y bus formation in terms of inspection method. Okay. By inspection, how can we generate Y bus matrix? When we have the Y bus information for any admittance diagram, we can generate Z bus from that. Okay, Z bus, this is the Y bus matrix. So Z bus will be something like the inverse of Y bus. So from that Y bus matrix, when we make the inverse calculation of the matrix, it will give us Z bus. Okay. This methodology to determine the impedance matrices, which is Y bus or Z bus, is known as inspection method. inspection method to determine the different bus matrix. Okay. How we can generate Y bus from admittance diagram. Say for example, if you have been given the simple circuit, can you shift that information to its equivalent admittance diagram? In general,
Sorry, inverse করতে
right. In general, circuit diagram information will be given in terms of resistance or reactance or impedance, right? So impedance diagram, you have to make the inverse to generate the admittance information. Okay, and in the source, generally we have used generator, but you know the source conversion from generate voltage source to current source. If it is voltage source, generator case, that voltage source will have impedance in series. But here you can see current source, which is the equivalent of that voltage source. If it is there, it is actually the generator, and the equivalent of internal impedance to its equivalent admittance. So you know already how to shift source conversion, right? If it is voltage source, how we can generate the equivalent current source? Voltage source will have uh, series impedance or series reactance, but current source will have parallel admittance, right? The equivalent parallel admittance. The source conversion concept in circuit course or DC circuit or AC circuit, basic circuit course, right? How we can generate source conversion from voltage source. If it is given voltage source, how can we shift that to its equivalent current source or vice versa? If it is by current source, can we generate the voltage source equivalent? So based on nodal equation concept, we can generate all these Y bus as well as Z bus. Okay. So self-admittance, sometimes known as, here you can see self-admittance and mutual admittance, driving point and transfer admittance. Sometimes they have different authors has mentioned in different books, like driving point or transfer admittance. That means self-admittance equivalent to driving point admittance and mutual admittance for transfer admittance in some other author or in different text. Okay. So I think you have got the clear idea regarding how to generate, first of all, the impedance diagram, then the reactance diagram after simplification, excluding load as well as shunt parameter like admittance and what are other resistance. These three you have to exclude to generate the reactance equivalent circuit of the impedance diagram. Then if admittance diagram is given, you can generate the Y bus based on nodal concept or KCL equation, node equation. And if we can generate Y bus from that, based on matrix inversion, we can generate equivalent Z bus as well, right? This is all about for today's discussion. Do you have any question?
স্যার এই টপিকটা কি কুইজে ইনক্লুডেড?
This topic regarding reactance diagram, the partial content is included, not the total. Like Y bus, Z bus is not. Okay. But the reactance diagram or admittance diagram, the earlier part of the lecture is included. How to generate the admittance diagram based on the per unit calculation.